So in this particular video we are going to discuss about the geodesic equation. So this is a very fundamental topic in the general relativity and the basics of it to understand all of the different complex thing. So in this particular video we are going to derive the geodesic equation using the different method. There are actually a lot of method. First method, you can say that with the help of the action integral. So with the help of the action integral we can calculate the geodesics, because generally geodesics is what the shortest distances between the two points on a curved surface. That's why the action integral principle is used. Then the second way is using the Lagrangian of the free particle. So this method can also be used to find out the geodesic equation. Basically what we are going to do in this particular video is that we are going to use this particular method. The more fundamental method is like the action integral, because generally the action integral is related with the variation principle, calculus of variation, in which we have to minimize the path, and that what exactly the geodesics is the minimum distances between the 2 points generally. So that's why the action integral principle is widely used, and you will see that in most of the books and the notes you will find that they derived it using the action integral. But ours is something like different. We will generally do this with the help of the Lagrangian method. So let's see with the Lagrangian method, and the Lagrangian method is quite also easy from the action integral. That's why this is method I'm going to use. And also this Lagrangian method is given in the David Tong's lecture note also, which personally I used it for the general relativity. That's why you can use this particular book for the David Tong. Okay, 1 minute. So you can use the David Tong lecture notes. Now let's start the derivation. So be careful with the indices and some of the basic rules that we used in the general relativity. First of all, let me clear that all of the notations that I will use here. First is this. So this is generally called the metric tensor. Okay, metric tensor, this is our first thing. And later when we will in the final stage of the derivation, you will see these type of notations, and this is called the Christoffel symbol. Then you will question that what is the use of this particular Christoffel symbol and the metric tensor and how they are related with each other. So the fact is that the Christoffel symbol used because when we move in the curved surface, you can imagine that this is our surface. Okay, it's just curved, not a straight line like what we have usually dealt in the real life. This is like curved thing. Okay, so when we're moving in the curved surface, your basis vector changes point to point. Okay, your basis vector changes point to point. Let me do in a more, okay, suppose that this is our curved space time. Okay, so in a flat space time that we usually deal, like in the general cases, you will see that the basis vector, which is I cap and j cap, are perpendicular to each other, and it is same throughout your particular space. But when you deal with the curved space, what will happen is that first of all this I and j will not be, you can say that this is our basis vector in x direction, this is our basis vector in y direction. They are not orthogonal. And to deal with this, we introduces the metric tensor. Now what will happen is that when you move, these basis vector also changes its direction, like in this direction, like in this direction, like in this direction. So it changes the direction everywhere when you will move through a curved space. And to measure this particular change, we use the Christoffel symbol. It tells us about that how the basis vectors are changing in a curved space. So this is what typically the meaning of the Christoffel symbol and the metric tensor. Metric tensor also can be used to measure the angle between the two basis vectors, because now they are not orthogonal like in the case of the flat space time. this is all you will deal in the differential geometry. For more clarity, you can see some of the books like the Prasoon Kumar Nayak book, the book that I recommend always to all one to discuss about the differential geometry. Okay, so the topic of video is not about the metric tensor and the Christoffel symbol. It's our main motive is to derive out the geodesic equation. So without wasting our time, let's start the derivation of it. So I have introduced you the Christoffel symbol and this particular metric tensor. Now let's see what we can do. First of all, we are doing with the Lagrangian method, so we have to show, or you can write out the Lagrangian. So Lagrangian will be m by 2 g and mu 1 minute, be careful with the sign convention. Okay, g mu nu, and here it will be q dot nu q dot mu. So generally this is our the Lagrangian, where you will argue that what is this, we aren't familiar with this. So because we are dealing with the Lagrangian and there is only kinetic energy, you can see that we can write this as Lagrangian is equals to 1 by half into mass into velocity square. And again, you know that we are not dealing with the general spaces, flat spaces, like we do in the Newtonian mechanics. We are dealing with general relativity where the space and time is curved. So you will see that the distances now between the 2 points on a curved space is measured by like dss square is equal to gij dsi dot dsj. 1 minute, this is subscript, this is okay, dsj. So you will see that this is the more fundamental form of writing out the distances between the 2 points on the curved space, where this is our metric tensor. Like I have said before, it's like the distances, it's like measure the angle between these basis vectors to know about that how our basis vector is performing and all that stuff. Okay, sorry for that. Okay, so these are all things. Just like this, to measure the distances between this, we define that the velocity square, like the velocity square can be written as gij, and I defined q as our position vector first for mu, q dot mu and q dot mu and q dot nu. So I will clarify that this particular symbol is known as nu and this particular symbol is known as mu. Okay, so these are the two terms. So this is how we define the velocity, and I've just put down this particular formula here. As you can see that I have used this particular formula. Okay, now I guess you have understanding of what this is. Now let's see the next step on taking. Okay, so you have our Lagrangian, and this is similar to the kinetic energy Lagrangian because potential energy is not there. 1 minute. Okay, so now what we are going to do is that we are going to take the derivative of this Lagrangian because Lagrangian equation. So first of all, we are going to take the derivative with respect to the q sigma. So let's start the derivative with it. Actually here the indices should be carefully written here. Okay, so when we do this, what we can do is that m by 2 and it will be del g mu nu divided by del q sigma, because this particular q mu and q nu are independent of the sigma, so we'll only act with this particular the metric tensor, and this is our equation, first equation. You can see that this is very important equation. Okay, now the second equation is like taking the derivative of this Lagrangian with respect to the q dot sigma, and now here the g mu mu acts like a constant, and we are like m by 2 g mu nu. First of all, we do the differentiation like this. It's like del 1 minute. Okay, so it's like del q dot nu divided by q del of q dot sigma, and here q dot this particular nu 1 minute here in this is You have to remark the indices and label the indices correctly. Okay, the mu and the nu looks like a very similar quantity, na? Okay, here it should be mu. So mu. Then plus we will do the take the derivative with respect to q dot sigma of this particular q mu. Remember, this is mu, okay, and this v like is nu. Okay, so plus then this q dot nu looks like a constant. Then we did, then this is the rule for the differentiation, the product, and then del of q dot mu and divided by q dot sigma. So as you can see that we have obtained the two equation here. This is the second equation, this is our first equation. First we have took the derivative with respect to q sigma, then the derivative with respect to the q dot sigma, and we obtain this particular equation. Now what we are going to do is taking the time derivative. Now we are going to do the take the time d by dt of this del L by del q dot sigma. So first of all, what I'm going to tell you before doing this is that see this particular quantity, like there is a symbol, like in the tensor when you study the notation, what we can do is that we can change our dummy indices. We can change our dummy indices and they are symmetric. So if they are symmetric, what you can see is that when you will interchange this particular indices, you will obtain the same thing. It means what I'm trying to say is that q dot mu divided by del q dot sigma q dot mu is equals to q dot nu del q dot mu divided by del q dot sigma. This is what I am trying to say, that these are two similar things. Why? Because the only difference is that the indices, when you replace the indices or change the indices, like replacing the nu with mu and mu with nu, you will get the same equation. It means these two of these particular equations are same. Okay, so these two are symmetric equations. So I'm going to add this up and let's see what will happen. So when you will add this, you will like that m by 2 g mu nu, and if these are symmetric equation, you can write this as 2 into q mu del q dot nu divided by del q dot sigma. This 2 and 2 will cut out, and in the next equation what you can do is that yeah, you are here with m. And another thing, this particular quantity, see this particular thing, this is also very important, because if you have studied, this is equal to the canonical delta sigma mu. How? Then you have to take the course on the tensor calculus and the tensor notation, because these are all things of the basic notation, that how to define the canonical delta in the tensor calculus. So if you see, this is equal to the canonical delta, writing this in the canonical delta g mu nu, and here canonical delta sigma nu, and here again q dot okay dot mu. Now if you know the property of the particular thing, which is the canonical delta, this mu and mu will get out, and what you are left with is mg 1 minute mg mu sigma q dot mu. Yeah, this is our equation that we are left with. So this is what? This is the derivative of our Lagrangian with respect to the q dot sigma. Okay, now what we are going to do is that taking the time derivative of this particular equation. So let's see what will happen. So taking the time derivative, which is d by dt of our this particular term, which is del L by del q dot sigma, okay, is equal to, first of all we apply the chain rule, and it will be m del g mu sigma divided by del t q mu, okay, and then taking our g mu sigma as a constant, and this will the double derivative and mu, Okay, now I'm going to do a one thing, so carefully see what I'm going to do here. If you have to define the velocity like q dot nu. What is q dot nu? It's the velocity, and q is our position vector, so it can be written as d q mu and divided by dt. So what I'm going to do is that I'm going to substitute this. Like how? So I can do that dt is equals to d q mu divided by q dot mu. So here what I'm going to do, putting this value of dt in this equation. You see what I have done? I have done like the time derivative of this position vector qv, or not v nu. So q nu is equal to the dq divided by dt, dq nu divided by dt. What I'm going to do, substituting this dt in this particular equation, let's see what will happen. Okay, so let's substitute this. So after substituting, what will happen is that it will look like this. Let's say we can denote it as d pi dt of del L by del Q dot sigma, and it is equal to the m del G mu sigma divided by, putting this dt, it will be del Q del 1 minute Q dot, not dot, 1 minute, not dot, okay, del Q nu multiplied with her q dot mu q dot nu, so q dot nu, and plus mg mu sigma q double dot mu. So this is what we got, and this is very, very important. This is the time derivative. This is the time derivative of our this particular term, which is the Lagrangian differentiation with q dot sigma, and this is our term that what we got. Now what we are going to do is that we are going to now use the Euler-Lagrange equation, which I hope you know what's the Euler-Lagrange equation formula. It's like the d by dt of del L by del Q dot sigma minus del L by del Q sigma is equal to 0. I have found this particular value, and the value of this is here. So now what I have only to do, put the formula. So what is the value of this? So if you will see, I have derived the formula as equation number 1. Okay, as you can see that this is our formula, where we take a derivative with respect to the Q sigma. We are going to substitute this, and let's see what will happen. First of all, this big equation we have to substitute. This big equation, you can see this big equation we have to substitute. So let's see what will happen. Okay, so okay this is very big equation. I guess I will copy this. So let's copy this. 1 minute. I'm gonna copy this equation. Let's see what will happen. Okay, so I can't find it. Okay, so left it out. We will write down it. Okay, so now the equation will be putting this particular value. Let's see what will happen. It will be like m del G mu sigma divided by del Q V, not V, it's nu. Okay, I'm also in very slope in this language. Q nu Q mu and plus m G mu sigma and okay Q double dot mu. So this is our this equation, and negative of our one another equation, which you will say it's like m by 2 del G mu v by del q sigma, and here it's like q dot mu q dot nu, and it is equal to 0. So this is our big looking equation. This is our big looking equation. Now what we have to do is that doing some of the calculations to take common. Let's see what we can take common. That's it, q. Okay. So first of all, I will cancel the mass term. Mass and mass will cut out. Then I will do is like that. So okay, now g mu sigma q double dot mu. Okay, this term is writing here. I am okay. This, and let's say common. So I guess plus, here it will be like del g mu sigma by del q mu minus 1 by half del g mu nu divided by del q sigma. This is our term, and like here q dot nu q dot mu, and this is of course equals to 0. Okay, so this is our whole equation that we have written. Now what we have to do is that so this is sigma. Okay, this is sigma. Now I'm also going to use again the property of the symmetric tensor. What I can do is that see this particular thing. So here del g mu sigma by 1 minute. Del g mu sigma divided by del q nu. So this particular thing can also be written as, this is mu, okay, can also be written as by changing the dummy indices, because it's valid in the general relativity. You can free to relate this and exchange this. What you will do is that you will shift this mu to the denominator. So now let's see what will happen. So when you will do this, you will be like del g v sigma divided by del q mu. 1 minute. Del q mu. So this is our thing, and these things are equal because from the symmetry rule. And if you don't know about this, you have to read some of the tensor calculus books. You will study that how to change the indices and all that stuff. So this is our thing, like del g mu sigma by del q nu is equals to del g, and you just change the indices. So can I write this as 1 by half of both of these the adding of these particular two terms? Yes, of course I can write it. Yeah, of course this is valid. So what I'm going to do is that I'm going to do is that let's see. Okay, so this can be written as 1 by half and 1 by half of these two particular two terms, and then see how our equation will lead us. Okay, so our first term was like g mu sigma, and here it was like q double dot mu. Okay, this was our term. And plus, as I have written here, that I can write down these two particular thing. As I have written, I can write down these particular thing as the sum of the two. Then this become very easy. How? So see how I am going to write this. So it's like that g mu sigma q double dot mu plus I can write this as the sum of 1 by half of del g v sigma by del mu plus 1 by half of del g mu sigma by del nu, and minus 1 by half of again this equation del g mu v nu by del q sigma, and again these terms which are like q dot and q dot mu, and it is equals to 0. So this our long looking equation, actually this become very long, I haven't expected to be like this. So this long equation, now we have to do some mathematics, or good mathematics. What I will do is that I will multiply this with the symmetric of the metric tensor, symmetric metric tensor, and let's see what will happen. Multiplying with symmetric multiplying g, I guess sigma and tau I will. So okay, so g tau sigma multiply with g mu sigma and q double dot mu plus g tau sigma, taking 1 by half as common. So in short form, how I am going to write this as del and mu g sigma plus del 1 minute. In the short form, I can write this as, if you multiply this equation with the symmetric matrix g tau sigma, you will here see that there will be g tau sigma, and the equation that you are left with the equation g tau mu this nu and into q dot this and q dot mu, and this is equals to 0. Okay, so this is our whole term, but remember these are the operations here I can use. This mu and mu will go down, and the thing that you are left with this is this mu, 1 minute, mu and tau, and this mu and tau when will act on this, I'm going to directly write this out, because you will eventually find it out that what I have done if you studied all the things in the good manner. This will be q double dot tau plus Christoffel symbol tau mu v q dot v and q dot mu is equals to 0. And finally, the equation that you are now seeing, this particular equation, what in that general relativity is called the geodesic equation. So it was a quite very lengthy thing. Then you will ask out that how you have written the del tau term. So see here, I'm going to write it how I have written it. Actually, here the thing that I have written, which is our tau, sorry, it's Christoffel. So this is called the Christoffel symbol, which I have mentioned earlier in the video, and mu. What is the value of this? So this is equal to j tau sigma. I guess this was the matrix that I multiplied. Yes, g tau sigma 1 by half of del mu of g v sigma plus del v q. Oh, why I'm writing it here? It will be q mu sigma plus del sigma, del sigma. I'm saying sigma, writing mu. I don't know what happened to me. And q mu nu. So this long looking like equation is what known as Christoffel symbol. Actually, when you will define the geodesic equation, you have to solve and find out the each and every component of the Christoffel symbol. How? Because as you can see that here is the summation of tau, mu and nu. So you have to choose each and every indices, like there are different components. You can say that like tau 122, tau sorry, gamma 122. This is symbol is called gamma. Okay, gamma. Christoffel said 211. I'm taking examples that there are different types of the components of this particular Christoffel symbol that you have to calculate. Okay, so this is all about the geodesic equation. It was a quite a painful derivation and a quite very long derivation, I can say, but yet we have derived it using some the Lagrangian of the particle. I guess when using the axiom principle, the equation is very short and you can derive it, but I have chosen the Lagrangian's perspective because it is not given everywhere. That's why I have done it with the Lagrangian's perspective, and we finally derived our geodesic equation. Be sure to check out the video properly because there are different types of the indices, things like we have done like the symmetric indices and changing the indices while developing this. So this is our first video. In the second video, basically what we will going to discuss is about the solving the geodesic equation, like, or you can say that we will discuss about the different types of the metric tensor in the general relativity, like the Schwarzschild metric, which defines the metric of the space time, like in a very high gravitational pull, you can say that. So we'll discuss and also the derive of that particular metric, but those topics are very advanced topic because the derivation of that particular topic can be done with the help of the Einstein field equation. And to understand it, you have to know not only about the metric tensor but also about the stress energy tensor and Ricci tensor, Riemannian curvature tensor and all that stuff. So at last I'm going to recommend again a book. So if you are studying something mathematical, differential geometry and all, I have recommended all the time, read Prasoon Kumar Nayak, or you can find any general relativity book. And I'm pretty sure that the mathematics sections will be also discussed in that particular book. I guess you can choose the gravitation book, or sorry, gravity book by James Hurtle, I guess, yes, by James Hurtle, or you can choose Our World. Our World is very nice, but it is only nice for those person who has done a lot of mathematics and wanted to know about that in a great detail, because each and every very detailed theorems of manifolds is given in that particular book. And that's why I will say that this Our World is for intermediate student, not for the beginner student, because they assumes that you know all about the basic stuffs and all that stuff. That's why. So this is all about the today's video on the discussion of the geodesic equation, and what we are going to discuss in the tomorrow video. So this is for today's video.